Hello students, we are going to be spending this lesson focusing on elements, compounds, and mixtures, and specifically how do we classify them. We'll spend a little bit of time going over the physical separation techniques that we use to separate out mixtures, and we'll also spend some time looking at the differences between physical and chemical properties, and what are some things that show us it's undergoing one or the other. So let's get started. We are going to first start off by focusing on the classification of matter. So if you remember when you took biology, which is the study of living things, there was a whole classification system for living things. And you might remember kingdom and phylum, class, order, and so on. Well, chemistry is the study of matter. So we have a whole classification system in chemistry to classify matter. So the first two big categories is whether matter is a substance or a mixture. Substances only has one type of particle throughout. In a mixture, you have two or more different substances, and I use that word substance specifically, that are only physically combined in variable proportions, and we're going to come back to that. So when we focus on substance, and I say it only has one type of particle throughout, it's going to be, when I use the word particle, a little bit general of a term because that particle could either be the same element throughout or the same compound throughout. So let me zoom in on the left-hand side, which is where we're going to focus on first with our substances. So substances will either be an element or a compound. An element is only one type of atom. So all atoms within an element have to be the same element. So one big thing that you're going to want to keep track of, though, is that we have monoatomic elements, which are most of our elements on the periodic table. So something like sodium or copper or neon, which is a gas at STP. But we also have diatomic elements. There are 7 of them. There's different ways you can remember this. I usually tell students Hober-Finkel, which is why I spelled it out in this format on here. You also have the phrase like horses need oats for clear brown eyes, or 7-Up, which I'll show you in class. These are 7 elements that do not exist as a single atom in nature. They're always going to be paired with another one. So we write those specifically out as like hydrogen gas would be H2, oxygen would be O2, and so on. So that's going to be really important when we get to equation writing. Now, compounds are 2 or more different elements that are chemically combined in fixed proportions. So most of you guys are familiar with H2O. That's a fixed proportion. Every 2 hydrogens have to be bonded to 1 oxygen. If I change the proportion, it's no longer water. And we can have compounds in the gas, solid, or liquid state, but that's going to be the only type of particle present in that sample is going to be one type of compound that's replicated. One other little thing with this, and it kind of shows up right above it, is that, your compounds can be separated by chemical means up here, while elements cannot. So that's one difference between elements and compounds. Even though they're both substances, compounds are the only one of those 2 that can be separated chemically. Particle diagrams are a great way to represent elements and/or compounds. Particle representations are a piece of our AP chemistry exam, so you want to start to get very comfortable with interpreting these. So over on your left are your elements. So in this particle diagram, we have an example of a monoatomic element. Not that you would circle this on yours necessarily, but what I'm showing you is that on here, this is one particle, and all the particles in that diagram match, so that would be make it a substance, and because they're all the same element, that makes it an element. In the diatomic one, you would just see 2 of the same one bonded together. In a compound, the particle here is, say, this compound here. Okay, we have 2 different types of elements bonded together, and when I look at the particle diagram, they're all the same compound, so that makes it a substance, and because I have 2 different elements at least bonded together, that makes it a compound. So you want to be able to interpret those, but also draw them, and something we'll work on in class. All right, let's get over to that mixture side. So mixtures are going to have 2 or more different substances. So that could be 2 elements mixed together, or 2 compounds, or an element or a compound, but they're all just physically combined, meaning that you won't see them bonded together. And they're going to be physically combined in variable proportions. So if you make lemonade, you could put 1 scoop of lemonade in your pitcher of water, or you could make or put 2. They're both lemonade, but they have different amounts of each part. That's one big difference from a mixture than if we compare it to a compound. So there are 2 big types of mixtures that you have to be aware of. The first one on the left-hand side there is a homogeneous mixture or a homogeneous mixture. You'll also very commonly throughout the year see these referred to as solutions. So these are mixtures that have a uniform composition. They look the same throughout. So it goes back to that lemonade example where as long as it's all dissolved, it's going to look the same throughout. Brass is considered a homogeneous mixture. It's an alloy, which we'll talk about, but it's a mixture of two or more different elements. It just happens to be a solid. It looks the same throughout. Salt water, as long as the salt is all dissolved, is also a homogeneous mixture. And I wanted to show you specifically, and this is really important, it's going to come up in our equation writing, is because I have this AQ here, okay, that is called an aqueous solution. That simply means that it is specifically mixed with water. So just be aware of that, and I would definitely jot that down for yourself. And we'll look at the particle diagrams in just a second. The other type of mixture is a heterogeneous mixture. This is not uniform. You can see the different materials. I always think of chocolate chip cookie dough. You can see the ice cream. You can see the chocolate chips. You can see the cookie dough. That would be a heterogeneous mixture. Sand and water is a common example, and a couple other ones that I listed there that you can use. So let's look at what the particle diagrams would look at. First thing is, most of the time you just need to be able to tell that it's a mixture. So in this one, I can see that, well, here's one type of particle over here, but they all don't match. Here's another type of particle. That right there tells me it is a mixture because I have two different substances just physically mixed together. They're hanging out in the same container, but they're not chemically combined. Same thing over on the right-hand side with this mixture. Here's one type of particle, happens to be a compound. Here's a different type of particle, happens to be an element. So this is a mixture of a compound and an element. The difference between these two is this one on your left-hand side is evenly spread out. They're mixed together. So that's your homogeneous or homogeneous mixture. Over on the right-hand side, you can see that I have kind of one element clumped together down here. I have my compound up above. So that's kind of showing this where they're clumped together. So we're going to consider that our heterogeneous mixture. Okay, so that goes over that first page of just how do we classify our substances and our mixtures. So if we look at the next page, this is specific to just mixtures, which can be separated by physical means. So for this, just make sure you're highlighting for yourself, this is just for mixtures. And because they're mixed together just physically, we can use physical techniques to separate them. So the reason why these are important is you're going to have to actually be able to apply these when you're asked about separating a mixture. So the first one is filtration. This is when you would take a mixture, you would pass it through a filter, and that filter would separate it by the particle size. It would hold on to or keep the larger particle sizes, and if some particles are small enough, they'll pass through the filter. This is a great way to separate a heterogeneous mixture, specifically something like sand and water. So if you have like a solid that's mixed into a liquid, this is a great way to separate that out. Evaporation is another type of technique that you can use to allow a liquid component of a mixture to separate itself from a dissolved solid. So this would be used for a homogeneous mixture, such as dissolved salt in water. You would allow the water to evaporate, or you could also use boiling to have it occur faster, and take that out, and then you'd be left with the salt that was originally dissolved into it. So that would be a different technique that you could use as well. These bottom two we will definitely come back to later in the year when we do solutions again, but I want to mention them here because they are physical separation techniques. The top one up here is distillation. This is separated or using a technique to separate by different boiling points. So usually we would think of using this, say for two or more liquids that were mixed together. We would heat it up. The one with the lower boiling point would boil out of the mixture first. So you'd actually, it would boil out first, and then it goes down this tube, it gets condensed, and then it gets collected over in this other flask. Then you're left with the one that has the higher boiling point. And we'll come back to that again later this year. The other one that you should be aware of is chromatography. And you did this probably in biology with like your leaf pigments. You are actually separating it based on a couple of things: the size of the particles, the solubility of the particles, and also something called polarity and how the particles attract to each other. So once we learn a little bit more about polarity, we'll be able to explain this a little bit more thoroughly. This is another way to separate out a homogeneous mixture. So really, when you look at homogeneous mixtures, there's a couple of options. So it's really about knowing the components of your mixture and what's going to be successful. I do want to mention there are ways to separate compounds, which can be separated chemically. So one example would be like electrolysis, where you use electricity to separate out the components. As you can see here, we actually have a chemical reaction. So this would be your compound, and then we would use electricity to separate it into its components, which in that case are your elements. So we'll talk about that later on as well. So last little part here that I mentioned when we started is we're going over properties and changes of matter. So with properties of matter, these are we have physical properties and chemical properties. Physical properties are constants about usually a substance, with some exceptions when we talk about extensive physical properties, but we can measure them without changing the identity or composition of it. We can use different tools in the lab to measure it. So extensive physical properties are ones that actually depend on how much you have in front of you. So like when you take the mass or the volume. The ones that we usually focus in on are those intensive physical properties. This doesn't depend on the amount. It's going to be constant no matter how much of it we have, and it helps us to identify what we have. So density, melting point, boiling point, solubility. And if you were listening, you heard me just say MP is how I usually abbreviate melting point, and BP is how I usually abbreviate boiling point. So you're going to see that a lot. So those are important intensive properties along with a whole group of other ones. Our chemical properties are ones that really just focus in on how do they react with other substances. So this would be observed through an actual chemical change. So chemical properties would be its flammability. Is it reactive with water, or acid, or maybe oxygen? Those would all be examples of your chemical properties. Now, in this next little part, changes of matter, you're going to see these little red arrows, and this is just because I'm really focusing on, this is how the AP has it right in their curriculum guide, and I'm highlighting them for you because this is something that you could definitely see explicitly tested later in the year. So a physical change occurs when a substance undergoes a change in properties, but not a change in chemical composition. So two big ones are changes in phase. So anytime, say, you're going to have a solid that's melting into a liquid, that would be a physical change. Or maybe you're going to have a gas that's undergoing deposition into a solid. Those would all be your physical changes. Another one that students don't think of too often, which I think is really important, is just simply like the formation of a mixture. When you dissolve salt into water, that is a physical change. We can take them back apart using a physical separation technique. And when we take them back apart, that is another physical change. So definitely be aware of that one as well. A chemical change occurs when a substance is transformed into new substances, usually with different compositions. Now, these examples are just examples of possible evidence that you have a chemical change. Chemical changes are going to be your actual reactions. So some possible evidence that may indicate that you have a reaction or a chemical change would be the production of heat or light. You might have the formation of a gas, which you would see with bubbles. You might have a formation of a precipitate, which is an important term, which is just the formation of a solid. And then you can even have a color change. Now, just because you're making heat or just because you're changing color doesn't mean you have a chemical change, but it's evidence that you might based on other things that you'd have to then analyze. All right, this last little part is going back to particle diagrams. Any physical or chemical process can be represented symbolically by balanced equations, and we can use our particle representation. So I just wanted to show you the comparison between the two. In a physical change, you have, I'm looking right here, the equation, you have CO2 going from a gas to a solid. This is a physical change because my formula is not changing. It's still CO2. The only thing that's changing is whether or not it's a gas versus a solid. If you look at our chemical one over on the right-hand side, here you have water that's going to decompose into hydrogen and oxygen. We're making something new. So that indicates a chemical change. You can also see in the particle diagrams, here I have my water, which then, or sorry, not water, CO2. So I have my CO2, which here it is in the gas state. And if I look over on the right-hand side, they're closer together, but I still have my CO2 there. So that's indicating, again, a physical change. If we look at our right-hand side, we can see that there's been a chemical change. We've had bonds that have been rearranged, which you might want to add. So bonds are rearranged. Oops. Keep running off the page. So one thing I also want to point out that you might notice is I still have a water here. And why is that? Well, if I take two waters here, okay, I can see that that makes these two hydrogens and these two. And I have two oxygens, and that gives me two oxygens over here. Well, this water doesn't have anything to react with, so it stays put. So this kind of gets into conservation of matter. We have to show that it's represented, it hasn't reacted yet, and just keeping track of our elements. So just something to be aware of and keep an eye on, because that shows up in a lot of multiple choice questions. All right, I know that was a lot of information. What I would suggest is you kind of just, as you end this video, take a piece of paper, kind of do a brain dump, and just kind of put down all the stuff that we went through, and then try out the practice that follows. Great job.